All right, next up, we have Matt Helmus from Temple University, a veteran of the SLF Summit, giving us an update on modeling. Take it away, Matt.
Okay, well, thank you, Julie. So I'm going to start off by talking about spotted lanternfly, because that is the point of this. Sorry, I'm getting um, and spotted lanternfly was first found in 2014, close to Philadelphia, and Temple University, where I'm at, is in Philadelphia. I'm going to be focusing on here we go. Be focusing on transport today, and when we think about transport, we're thinking about eggs primarily. Eggs are commonly laid on stone, wood, metal, trains, pallets, containers, all kinds of things. Probably it was landscaping rock with eggs that were imported from China back in 2012ish or so that probably started this entire invasion. When we think about establishment, we think a lot about host plants, and it's already been mentioned several times today. The tree of heaven is an invasive, preferred host. It was actually first imported and planted in the U.S. back in 1784 in Philadelphia, and so when lanternfly arrived, a couple hundred years later, that is when it found tons of tree of heaven growing in the environment, and it was able to establish pretty readily. As far as impacts, there's a lot of talk about grape. Grape is the major agricultural impact that we've seen. But we also get these population explosions that occur. This is all from Ohio over the last couple of years, for example. And then also there's ecosystem impacts. And so I'll be talking about other species that will be feeding on the honeydew, just like what we heard in the last talk. But it's not just me who's done this work. It's really a team at Temple University, Jocelyn Bem and Benjamin Seibold. And together we do field biology and data science and mathematical modeling. And I say we do that, but really it's our team of students and postdocs and research technicians. And so all of these all these people here have contributed to the research I'm going to show you today. And then all of our work we try to make accessible to stakeholders and to the public. And so we produce a lot of apps that are online, and you can find these apps here at this website. The QR codes will take you to the particular websites that I'm showing or the particular studies that I'm showing too, if you're interested in reading about them. So I'm going to start off with talking about collaborative data science that we do, and I'll go through each one of these in turn. So lots of groups and agencies are surveying for spotted lanternfly. And a couple years ago, we put together a framework to compile all this data into one open access source. And so we collaborate with different groups and agencies, both federal and state agencies that collect those data. We then process all those data. We have a processing pipeline where we process all the survey data from these groups, and we clean them. Then we anonymize all that survey data around the coordinates, remove any sort of personal identifiers, et cetera. And then we release this data as open access as an R package and some code available with it. So right now we have over 1 million official survey records, and this is just my call to please use these data. They're easily downloadable. So before any of you are making any maps or running any models or anything, please download these data and use them. And of course, if you have questions about the data, contact me or check out the website that we have. And then for those of you who collect data, those agency personnel who collect data, please contribute data to this project. We're currently in the process of updating the database for 2026. We'll use whatever data it is that you have. Data are stored securely, they're anonymized, and really more data means better models for the US, Canada, and really the globe. So how do we use these data? The first way that I'm going to show you how we've used these data is by estimating diffusive spread rates. So diffusive spread, this is that phenomena where you have spotted lanternfly and sort of spreading out from a central source. And based on theory and looking at lots of invasive species, people have identified that diffusive spread rates tend to vary over time. Typically, you get sort of a lag phase in that spread rate, then you get massive spread rates that are very fast, and then you get a saturation point that occurs. This is work done by Joe Keller, a postdoc who's currently in my lab. He developed a method for how to do this. I'm not going to go through all of this, but basically he was able to develop a method to delineate the spread ranges and then able to forecast then this diffusive spread rate. So what he found was that in 2015, that is the year when we sort of saw this lowest diffusive spread rate right at the very beginning of the invasion. The highest diffusive spread rate that we saw was in 2020, and it was almost 30 kilometers per year, and then it's actually slowed since then. And so we've seen an increase in spread rate, and around 2020, we're starting to see a decline. And that's consistent with um, uh, multiple potential phenomena. We don't exactly know what's going on here, but the increased control efforts that all of you out there have been doing, all the agencies have been doing in the public. Regional saturation is also consistent with this, and also an edge diffusion effect that this is just sort of what happens with invasive species over time. That's not really the whole story. This diffusive spread rate is really can be contrasted to jump dispersal spread, and that's really what we're worried about today. So jump dispersal spread, this is that accidental long distance transport events. They tend to accelerate spread. And a former postdoc of ours, Nadej, developed a software R package that will estimate these jump dispersal events for any invasive species, but we've applied it to spotted lanternfly. So here, let's focus just on a subset of these data so I can talk you through how this method works. So here, this is a subset of the data. We've got these established populations here from the data set, all these gray circles. The first step is to run a clustering algorithm to cluster those occurrences. You then identify where the invasion front is, and you identified here, okay, well, here are three different new groupings or clusters here, for example. We're going to ignore the clusters that are older clusters. And then we're going to optimize that cluster size. And then in the end, then we can identify, say, 4 jump dispersal sites, for example. And so doing this method and variations on this method, the first time that we can see jump dispersal events in the data was in 2017. And by 2022, for example, we're getting lots of these jump dispersal events. And so while that diffusive spread that I showed you, was declining a bit, the jump dispersal spread through time, what we're seeing is accelerating. And so really what's driving the invasion now are these long distance jump dispersal events. And we're seeing that in the data set. But the question really is, okay, for having these long distance jump dispersal events, can we predict them? And so what types of properties then are associated with these jump dispersal events? So here's all the jump dispersal events that Nadej was able to identify since 2022. And what we want to know is if these jump dispersal events are in close proximity or right on top of some type of invasive species transport hub. And these are properties where the convergence of vehicles, goods, and people, they facilitate jump dispersal by, in our case, we're focusing on spotted lanternfly here. But agencies are really good. They have either a formal or informal survey list of hubs. So whenever they send their survey teams out, they're looking at these types of properties already. And so here's, for example, a list of those hub types. So we built an invasion hub spatial data set of all these different hub types that our collaborators use to try and survey for spotted lanternfly. And then we want to know if these hub properties, if these property types are associated with the jump dispersal events. So I'm going to walk you through how we do that statistically here. So say, for example, we have a spatial pattern where we have jump sites and they're pretty close to an invasion hub. And let's say that these are shipping distribution centers here. So if you look at it, you're like, okay, yeah, probably shipping distribution centers are where jump sites are found, and so we should go and survey those. And agency surveyors, they know this. They use that proactive survey list already. They're proactive, they're good at their jobs, and they direct crews to look at these where they think are likely going to have the proactive survey list. But the problem then is that in the data set, we're getting these data set from the surveyors, there's bias in that data set. And what happens then is that if you're only focusing on, say, one type of hub, say shipping distribution centers in this simple example, you might miss potentially other higher risk hubs because you're not looking for them. And so that means that that LiDAR data set that we're looking at has a sampling bias to it. We have to account for that sampling bias when we're really statistically trying to estimate what properties really are associated with jump dispersal events, or whether it's just a spurious correlation. So we did this by comparing different simulations to the data. Our first simulation was just a random spatial sampling, where basically like if surveyors went out and sampled randomly across the landscape, how far on average is the distance between these random survey points and these potential invasion hubs that we've identified. We then get a distribution of distances. This is, we'll call it a null distribution then, that we can compare our jump distances to. And then in our second simulation, we explicitly simulated this proactive spatial sampling, which is what agencies do. They go out, they're proactive, they're looking for these different jump dispersal events. And again, we can measure the distances here and create a null distribution. And then finally, we can compare the distances of the jump dispersal events that we've identified previously and compare those distances and ask then if those distances are lower to these hub types than expected from these other two simulations here. So if the observed jump sites in our case are closer to shipping distribution centers, then we can say, okay, these jumps are statistically associated with them. And so that's a really important key here. We're accounting for this sampling bias. So here are all that list of those hub types, those property types here. And what we found was that by correcting for this sampling bias, we found 12 key jump pathways. So no matter what, all these green distributions here, that's that random surveying simulation that we ran. All of those were then closer to all the hub types than expected by chance. And that indicates that there was this sampling bias in the data, which is what we expected. But after accounting for this bias, there are 12 hub types that were associated with jump events. I'm going to go through those now. So these were the hub types that are associated with the jump events: shipping distribution centers, for example, landscaping businesses, importers, and then others. I wanted to highlight one, though, that I thought was interesting: truck rentals. This is like U-Haul truck rentals. Those were associated with jump events. And I'm not certain that that's always on our radar when we're thinking about surveying. There are property types that weren't associated with jump events once you accounted for this sampling bias. Wineries, for example, amusement parks, and then also a lot of the sawmills and timber producers, those that are producing lumber for export, et cetera. Those, we didn't find any evidence that they were associated with jump dispersal events. And then we also looked at rail and road density because we have a pretty good intuition that probably there's a relationship. We looked at the density of either rail or density of roads around jump dispersal events. And so the density was much higher for the jump dispersal events than in our two different null models. So we can put all this together in a machine learning model, in ensemble random forest models, and then we can create a risk map that we can apply to different regions of the United States here. And so we're just going to look at Erie County. So here, for example, this is a county that we're quite worried about getting spotted lanternfly. Julie mentioned this in the talk at the very beginning of the day. And so here we have a very fine scale map, and we can resolve this to a very, very fine detail. And we're putting these maps then on transport hub risk map apps that we developed for different parts of the United States. And so here, for example, is the Erie one. You can zoom in and zoom out, find different locations that are potential hubs, and then direct your survey crews or your citizen science operations to these particular places. So I'm going to move away from the transport side and think a little bit about impact and establishment. We're going to talk about population size and individual movement. So we performed a photo mark recapture study. This was, again, I say we, but really it was driven by Katie, who was a former undergraduate with us and then a technician. And what she did was she went out and she photographed adult spotted lanternfly on trees for about 8 weeks. This was, in the fall when students had returned to campus for September through November. And they had, in her data, she had 21 red maples, 5 sites on Temple University campus. Temple University campus is about 20 hectares. She went out 4 times per week. She went out 2 times per day. It was a lot of work. She took over 3,000 photos. And so this is the system here. It's a very heavily developed urban system with very minimal green space. And this, for example, is one of our sites. It's right behind the biology department building. These are the red maples that she sampled. Then she identified individuals with fingerprinting. So every adult spotted lanternfly has its own unique spot pattern. This was developed again by Nadej and Jocelyn Bem. And if you're interested in that, take a look at this study here. She digitized all these photos using an i3S software. And then she compared the spot patterns to identify individuals of all the different photos that she took. And so in that way, then we can count the number of actual individual lanternfly that are on Temple campus. She found 1,000 unique individuals, and she had an incredibly high recapture rate. She recaptured over 50% of the individuals. And so with that recapture rate, then you can do actual population size modeling. This isn't just abundance, this is like the actual population size estimates that we can get. And so we estimated about there to be about 10,000 lanternfly in 2023 on Temple campus. So it's about 500 to 600 individuals per hectare, for example. And so this is a pretty high number for Temple campus when it just has a minimal amount of green space. The proportion of recaptures increased through time. And so I'm just pointing out that this is September through November. This is not July. This is not August. This is September, November. And you can see here that the single captures, this is just where we saw an lanternfly once, decreased quite rapidly. And we kept getting lots and lots of recaptures, where at the end, we're basically getting more or less all recaptures. The individuals were observed for an average of about 9 days, and most of the individuals that we saw were observed for less than 2 weeks, but we did have a couple individuals that were able to track for 6 weeks, a little bit over 6 weeks. About 99% of the recaptured adult lanternflies showed very limited movement. Again, I'm pointing out when this study was done. 75% or so, about 2/3, just stayed on the single tree that we first found them on. About a quarter moved trees, but they stayed within that site, so they just moved to the trees that were next to each other. But there were, a small number that moved sites. It was 7 individuals that moved across campus to other sites. And so here what I've got is just the date here, and then I've got the individuals 1 through 7 listed here, and then these are the sites, and it doesn't matter what the site names are. But the one thing that I want to highlight is there are 3 individuals here that all moved between the same 2 sites simultaneously. And so some sort of evidence there might be some type of coordinated movement going on there. This is a small sample size, but we did see that, in 3 out of 7 of the individuals that moved sites. So we're going to move from this idea of population size in these urban environments to vineyards and vineyard impact, and thinking about optimal thresholds, which we'll be hearing a lot about over the next couple days. And in this particular piece of work I'm going to talk to you about, we really want to ask the question of, does local scale and movement influence optimal thresholds that growers use whenever they're deciding when to spray? So there's movement that occurs from lanternfly, from the surrounding vegetation into the vineyards. And then what happens then is there's monitoring that occurs until a particular threshold number per vine is reached. And then that threshold number then indicates when the grower should do some type of spraying, some type of control effort. So this work was done completely using mathematical first principle models. And this is Jacob. He's going to defend in 2 weeks, so he's rushing to get all this put together in his thesis. And he built a 3-stage local scale diffusion movement model that has seeking, a feeding, and a flying stage that mimics the known behavior of lanternfly adults and was parameterized based on a lot of studies that other spotted lanternfly researchers have actually made on lanternfly. And so the objective here then is to try and minimize the time that spotted lanternfly spends on vines. And so we're looking at the density of lanternfly times the number of days that are found, and we're trying to minimize that number in some way. And that's sort of our optimal control objective. So this is just a very simple simulation. I'm going to show you just this one, but we have other models that actually run real simulations in real landscapes across vineyards, for example. And you can see that this is the vineyard here, and then this is the forest, and this is the edge, and there's a buildup that occurs of lanternfly right here along the edge, and it builds up pretty quickly. And so I'm going to compare a no treatment simulation to 3 different simulations with 3 different thresholds, and we're going to monitor, a vine that's here on the edge. So the no treatment here, we've got the population in the vineyard, we've got the time over days, and it's really the impact is the area under this curve, what we're trying to make smaller or minimize. So in simulation 1, we're going to say, okay, we'll spray whenever you see, 10 spotted lanternfly per vine, and you get a percent reduction of about 40%, which isn't so bad. If we wait a bit longer, though, and we spray at 50 spotted lanternfly per vine, we get a 60% reduction, which is better. And then if you wait too long, for example, and you wait for 100, you only get like a quarter of that. So you get 25% reduction or so. And so what this simulation indicates, and we've run lots of different simulations, this is the simplest one so far, is that the optimal threshold isn't just a single number in this simulation, in this mathematical model that we're finding, but it also depends on timing. And so these thresholds depend both on the spotted lanternfly density per vine, but also when you're going to spray. If you spray too early or if you spray too late, it's not as good as spraying, right at the optimal time. And the reason this happens, why does this timing matter, is because the movement into vineyards, according to this model that we have that's been parameterized on real data, has a fast and a slow phase. So here's our model again. This is the start of the simulation. Here we're looking at distance invaded to the vineyard through time. And after about a week, we get a rapid increase in the distance here. So there's a big buildup that happens very, very quickly. But over time, you get a slowing of that incursion of lanternfly into the vineyard. And so what that means is that when you're thinking about enacting control, according to this model, when you're thinking about acting control, you have to, one, really be monitoring your vines from that edge to the interior. And you need to wait until that edge fills up before you spray. Because if you spray too early, you're going to miss all that buildup that's still occurring. And so you want to spray once that rate of incursion slows down. And so edges seem to be really important for lanternfly, both in the model that I showed you, but also researchers have thought this for quite a while. And so a postdoc of ours, Owen Snyder, went out and asked this question of, do spotted lanternfly really prefer the edges? Are they found more often the edges? Chose 10 sites. They are all adjacent to vineyards. He sampled in 5 different broad plant community types across the mid-Atlantic. And all these sites were in forest or forest fragments from the edge of a vineyard into the forest. He had a plot that was on the edge, a plot that was in a transition zone, and a plot that was in the interior. He went and he observed lanternfly from first instar all the way to adults. He measured all the different plant species that were there. And what he found was that, yes, spotted lanternfly are definitely most abundant at the forest edges. Each one of the lines here is one of his sites, and this is sort of the average here. So this is the edge of the vineyard, and this is the forest interior. And so while intuitively, a lot of us who worked on lanternflies for a while think this is, evidence that this is actually the case. And the reason he's found is that they're on the edges because they prefer the invasive hosts that are found on the edges. Again, this is intuitive, this is what we thought, but we haven't really seen data on this yet. The most preferred hosts were Oriental bittersweet, tree of heaven, and porcelainberry, and those are found typically on the edges. And those are the species that really driving this pattern of spotted lanternfly on edges. The edges also have different environmental characteristics, but that does not seem to be as important as just there are the hosts that spotted lanternfly like, and they're found on the edges. So now I'm going to talk to you finally about the response of Hymenoptera to lanternfly, thinking about ecosystem impacts. So they produce this sugary resource subsidies. They produce honeydew. We just heard about that. But also they produce feeding wound exudate. So they drill into the bark, and then when they leave, this sap, this exudate will actually ooze out. Stephanie Cannon, who just graduated, wanted to ask this question of what animals are feeding on spotted lanternfly, these resource subsidies. She had 43 study plots. She did 3 surveys. She did 129 total, she did 3 survey periods, 129 total surveys. She did collections of photography, and she collected a bunch of environmental data for each one of the sites as well. She had about 1,500 feeding observations. All the feeding observations that she had were invertebrates. She didn't see any vertebrates feeding at all. Less than 1% were beetles, true bugs. This is a Japanese beetle here, butterflies, katydids, some snails, and some harvestmen as well. About a quarter of the observations, about 20% or so, were the flies. There are lots of different fly species feeding on this honeydew. But the vast majority were Hymenoptera. This is over, 2/3 of the observations were Hymenoptera. And so I'm going to, we then dug in a little bit deeper with Hymenoptera and identified a lot of these species. So the 9 Hymenoptera families listed here were the most commonly observed. And lucky for the ant DNA work, the ants were the most commonly observed family, followed by the vespids and the apidae. So ants were the most observed subsidy feeders, and the species that was the most observed was this winter ant, and they are those ones that you saw in the previous study that had those big abdomens that will fill up with nectar or fill up with sugar, in this case, fill up with honeydew. She also found a really neat behavior. There's one of these ant species. This is a carpenter ant, and it's tending this fourth instar. It runs up, it taps really quickly, it grabs that droplet, and then it takes it back, to its nest. And so there's some really neat ant behaviors that were also observed. Social wasps were the second most important, and they included both native and introduced species. Here, there were the European hornet was found quite a bit, the German yellow jacket, and also the European paper wasp was also found. And then bumblebees and European honeybees were also common. She put all this together in a redundancy analysis, and looked at if lanternfly biomass was affecting community composition, and it was. It was the strongest environmental variable that was measured, explained composition of these Hymenoptera, and the invasive German yellowjacket was the most strongly associated species here. And so there's certainly something going on with these Hymenoptera species feeding on honeydew. And so in conclusion, I told you a lot, but just to sum it up, we are finding that diffusive spread is slowing, but that jump spread is accelerating. It's slowing, but these new satellite populations are emerging faster and also farther from the core, and that's what's really driving this. And then jump dispersal risk can be predicted spatially, and so we can develop these risk maps, and we have these risk maps, and we're putting them into apps. These late season adults that we measured on Temple campus, they exhibited very limited local movement. Most of those recaptured adults remained near that initial red maple that we surveyed. Some exhibited maybe possible coordinated movement, but about half of the observed spotted lanternfly at the very beginning of the study were only seen once, and so we don't know what happened to those, where they went. Population sizes in these urban landscapes can be very high, and now we have a way to actually measure population size as well. These optimal volume thresholds, when we're developing for lanternfly, we have to think not just on the number, the counts, and the density, but also the timing of when it occurs, because these thresholds are influenced by the surrounding movement dynamics of the system. Forest edges amplify this vineyard invasion risk as well. So we now know that abundance really is highest at the forest margins, and that's because that's where the invasive hosts are that they like. And then finally, we're seeing evidence that this spotted lanternfly, they're subsidizing these arthropod communities, but we really don't know how this affects their population dynamics, and so a lot more work needs to be done. Okay, thank you everyone, and please check out the website if you have any questions or are looking for any of the papers that I talked about today.
Great. Thanks so much, Matt. You have some questions in the chat, but I'm going to hit you with one. In the Winger printing study, were you able to use size, or did you think about using size to try to differentiate between males and females? Because I think that could explain some of your story.
Yeah, I literally asked the professor who's on that grant. I asked her that today, and at this point we don't have those data. Yeah, the undergrads that we had processing it didn't try and identify sex at all, but we do have those photos, and so I think it's something that we'll probably put an undergrad on to try and get that, because I think that's a really open question about it.
Yeah, I think that's probably doable too with the questions, at least for a good proportion of them.
Cool, thank you.
And I'll go ahead and read one of the questions here from Wendy McFadden to take it to Canada here. Would, in terms of your jump dispersal events, she asked, would ships also be associated with jumps? And I don't know if I saw that in what you did or not.
Yeah, we probably, maybe, I don't know, we didn't test ports explicitly because it seems like a lot of times it's sort of the ships moving crates of objects that might have lanternfly on them. We didn't look at ports themselves. I'll have to check on that and make sure that what I'm saying is correct, that we didn't look at ports, but I'm pretty sure we did.
Okay, great. And then we'll do one more here. Jules Amanita asked, has your research differentiated between sites that are likely to be the origin point versus the end point of your jump dispersal events?
Yeah, we assume that points that are the origin are those in sort of the old clusters somewhere. We don't really know where that is. And then if we get a new survey that occurs, say, in 2025 versus 2024, so it's a new blip that sort of comes up, then we assume that then is the end point. But we can't really trace back and say, okay, this came from XYZ. That would be maybe more, a DNA analysis or something.
Okay, great. Thank you so much. You have a couple more questions in the chat, but with great having you, great work, and you did a really good job of integrating across all of the different projects you have going on. So thank you.
Great. Thank you, Julie.